Okay. So good morning everyone. So first of all, let me know whether audio and video everything clear. So good morning everyone. So let me know whether audio and video everything clear, right? Okay. So if it is not clear, please let me know in chat box here, right? So give some comment in chat box if it is not clear. Okay. Okay. So we are dealing with the subject electromagnetics, right? So in electromagnetics we are dealing with the topic transmission lines. Okay. So in transmission lines we have seen different types of transmission lines, that is two parallel wire line and coaxial cable and microstrip transmission line. So these are the different types of transmission lines which are operated at different frequencies. Yes or no? Okay. So that's what we have seen here. Next, after that, in transmission lines I have told that we are not going to study about a particular type of transmission line. We are going to study about the transmission lines in general. Okay. So that means we are going to consider the transmission line as what? As two conductors separated by what? Separated by some dielectric medium. Okay. So this is how we are going to deal with the transmission line. So that's what I have told in the previous sessions, right? Okay. Okay. So what are the basic concepts that are needed in order to understand these transmission lines is nothing but transit time effect. So the first topic is transit time effect, and we have covered this transit time effect in the previous session, right? So we have seen transit time effect. So next, what is the another basic concept that is needed to understand these transmission lines is a distributive nature. Is nothing but distributive nature along the transmission line, right? Okay. So in the previous session we have covered this transit time effect topic here. We have covered this transit time. What do you mean by transit time and what are its effects? Understood. So why we are neglecting this transit time effects when dealing with circuit theory or network theory, and why we are including this transit time effects when we are dealing with transmission lines. So all these things I have explained in the previous session itself, right? Okay. So next topic is distributive nature along the transmission line. Next we will see distributive nature along the transmission line. So before going to this one, I will just revise here. I will just revise whatever we have done in the previous session. Just I will give a summary of the previous session here. That's it, right? Okay. So so at low frequencies, we have seen that at low frequencies, such that, what do you mean by low frequencies here? Such that L by lambda or TR by T ratio, L by lambda or TR by T ratio will be what? Will be negligible. So in this case beta L, what is beta L here? Beta L is nothing but the change in phase over length L, yes or no? So in this case beta L can be what? Beta L can be ignored. So beta L represents what? Beta L represents the change in phase over length what? Over length L. Understood? Okay. Okay. So that means we can ignore the phase shift between what? Between source and load. Understood? So that is beta L, right? Okay. So once we ignore the beta L, then in this case we have seen that so this is source and this is load and this is along the transmission line, Understood? So at source we have seen that the voltage will be what? V naught cos omega t, and on the transmission line also it is what? V naught cos omega t. At load also it is nothing but what? V naught cos omega t. So once we ignore beta L, then we have seen that the voltage at source and on the transmission line and also at load, everywhere it is going to be what? Everywhere it is going to be same. Understood? So at each and every instant we have seen that we have seen this graph here, yes or no? So this is at source and this is at load. At each and every instant of time, at each and every instant of time, the voltage along the transmission line, the voltage along the transmission line is constant. Yes or no? So that means the voltage is independent of what? Is independent of length of the transmission line. So whenever we are dealing with what? Whenever we are dealing with low frequencies. Understood? Okay. Okay. Yeah. So similarly, we have seen at high frequencies here. Whenever we are dealing with high frequencies. So at high frequencies, see, I have already explained all these things in previous session here. In the previous session clearly. Okay. Here just I am revising those things. That's it. At high frequencies, what do you mean by high frequencies here? At high frequencies such that L by lambda ratio or TR by T ratio. L represents the length of the transmission line, lambda represents what? The wavelength of the signal. Understood? And TR is the transit time and capital T is the time period of the signal. Right? Okay. So at high frequencies such that L by lambda ratio or TR by T ratio becomes what? Becomes significant. So such type of frequencies we are calling it as what? High frequencies. Okay. So you have to choose the frequency such that L by lambda ratio or TR by T ratio becomes what? Becomes significant. So those frequencies we are naming it as what? High frequencies. Understood? Okay. So under this condition here, so whenever L by lambda or TR by T ratio becomes significant, in this case beta L is the change in phase over length L, that means it will give you the phase shift between what? It will give you the spatial phase shift. It is going to give you the spatial phase shift between what? Between source and load. Yes or no? Okay. So here this spatial phase shift between source and load will become what? Will become significant. Beta L will become significant. See, in the previous session we have seen that this beta L, we can write it as what? 2 pi into L by lambda, or we can write it as what? 2 pi into TR by T. So this L by lambda ratio or TR by T ratio becomes significant, means this beta L will also becomes what? Beta L will also becomes significant. So once beta L becomes significant, then in that case what will happen here? So if you consider source and this is load. Okay. So what is the voltage at source here? Let us say the voltage at source is V0 into cos omega t. So on the transmission line the voltage will become what? V0 into cos of omega t minus beta x, and at load what is the voltage? V0 into cos of omega t minus beta L. So in the previous case we have neglected beta L and hence we have neglected beta x. Understood? We have neglected the change in phase along what? Along the length of the transmission line. Understood? But here since beta L has become significant, we should not neglect the spatial phase shift. Understood? So in this case, funny, good morning funny. Okay. So in this case if you draw the voltage here, along the transmission line, okay, so let us say this length here, this length of the transmission line is L. So this is at source, this is at load. So if you consider, we have considered that, let us assume now here beta L is significant. We have assumed that, let us assume beta L is 90 degrees, r pi by 2. So in this case we try to draw what? We try to draw the voltage along what? Along the transmission line. So what we got here? So whenever beta L is equal to 90 degrees, what will happen? At omega t equal to 0 here, so at this instant how the voltage will looks like along the transmission line? So at omega t equal to 0, at source the voltage will be what? The voltage will be V0, and at load the voltage will become what? Put omega t equal to 0, what you are having? 0 minus what? 0 minus 90 degrees. So cos of minus 90 will become what? 0. So at load you are having what? 0 volts. At source you are having what? Maximum voltage, that is V0. So along the transmission line how the voltage will be? Here it is maximum and here it is minimum. So the voltage along the transmission line is going to vary like this. Now if you observe at this instant at omega t equal to 0, if you observe the voltage is not constant here. Along the transmission line. Now the voltage is varying along the length of the transmission line. That means here the voltage has become a function of what? Become a function of length. Understood. Now, if you consider at another instant of time, let us say omega t is equal to 90 degrees here, omega t equal to 90 degrees. So, at this instant, what will happen here? At omega t equal to 90 degrees, what will happen? So, at omega t equal to 90, the source voltage will become what? 0, and the load voltage will become what? V0. Yes or no? At omega t equal to 90, you are going to have 90 minus 90, so cos 0. So that means here you are going to have the maximum voltage, and here at the source you are going to have minimum voltage. So that means the voltage at this instant, the voltage along the transmission line is varying in this manner. Understood? So this is at omega t equal to 90 degrees. And this is at instant omega t equal to 0 degrees. Understood? Okay. Now, if you observe, this is at one instant of time and this is at another instant of time. So that means with respect to time also, the voltage is what? The voltage is varying. So that means here the voltage is a function of what? Is a function of both space as well as what? As well as time. Understood? Okay. So like that here, for different instants of time, if you try to draw the voltage along the transmission line, it will become a function of what? It will become a function of both space as well as what? As well as time. So this will occur at high frequencies such that L by lambda ratio or TR by T ratio becomes what? Becomes significant. Understood? Okay. Okay, yeah. So I have told that whenever this voltages, you can analyze the same thing with respect to current signal also. So then we are going to get what? The current will also become a function of what? Length and time. So that means it also becomes a function of space as well as what? As well as time. Understood? Okay. Okay, yeah. So because of this, what will happen here? Because of this, what will happen? Once the voltages and currents becomes the functions of both space and time, then in this case, you cannot apply what? You cannot apply KVL and KCL. KVL and KCL are ruled out. You should not apply KVL and KCL. KVL and KCL. Understood? So whereas in the previous case, at low frequencies, the voltage is constant over the length of what? Over the length of transmission line. Here the voltage is a function of what? Only time. This is at omega t equal to 0 degrees and this is at omega t equal to what? Omega t equal to 60 degrees. Let us consider. This is V0, this is V0 by 2. Understood? Okay. So the voltage is constant over the length of what? Over the length of transmission line for each and every instant of time. So here the voltage and currents becomes the functions of what? Only time. They are independent of what? They are independent of length of the transmission line. Understood? Okay. Okay. So here you can happily apply what? Here you can happily apply KVL and KCL. KVL and KCL are valid in this case. Understood? Okay. Okay. So at low frequencies, what we have concluded? At low frequencies, transit time effects can be what? Transit time effects can be neglected. Transit time effects can be ignored or can be neglected. Understood? Okay. Okay. Whereas at high frequencies, transit time effects will become what? Will become significant. Transit time effects becomes what? Becomes significant. Understood? Okay. Okay. So I have explained here why we are able to apply KVL and KCL here, whereas why we are not able to KVL and KCL in this case. All these things I have explained in the previous session itself. Okay. So please go through them here. Please go through them. Right? Okay. 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 So this is all about transit time effects. So next we will see distributive nature along what? Along the transmission line. So here we are going to deal, whenever we are dealing with the transmission lines, the voltages and currents will become what? Functions of what? Functions of space as well as what? Space as well as time. So that means here whenever we are dealing with the transmission line, we are considering that L by lambda ratio or TR by T ratio will be what? Will be significant. And beta L is also significant, and hence beta L is also significant. Understood? Okay. So that's why voltages and currents will become functions of space and time throughout our what? Throughout our transmission lines. Understood? Okay. 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 So we are going to deal with the transmission lines at high frequencies such that L by lambda ratio or TR by T ratio will become significant, right? Okay. So next we will deal with the distributive nature along the transmission line. So next concept, if you want in detail to understand transit time effects, please refer previous lecture here, right? Okay. Just I have revised whatever I have done in the previous lecture, just I try to revise all those things, that's it. Okay. Okay. So next topic here, that is distributive nature along the transmission line. Distributive nature along the transmission line. Okay. Along the transmission line. Okay. So here let us say this is source, and here you are having load. So this is the length of the transmission line, and let us consider this axis is x-axis. So this is a let us consider this is x-axis, right? Okay. Okay. So the length is L. So let us consider this is x is equal to 0 and this location is x is equal to L, right? Okay. So now see here. Now if you consider a conductor here, let us consider a conductor. So what is the resistance offered by a conductor here? So in general, we know that whenever we are dealing with DC here, understood? Okay. So what is the resistance? What is the DC resistance offered by a conductor here under DC? Under DC or at low frequencies. The resistance we are going to consider it as what? DC. So DC or at what? Or at low frequencies. See, I don't tell every time what do you mean by low frequencies. What do you mean by low frequencies here? Low frequencies means such that L by lambda ratio or TR by T ratio can be neglected. That must be fixed in your mind. Okay, whenever I am saying low frequencies, you have to understand that L by lambda ratio or TR by T ratio can be neglected. Understood? So whenever I am saying high frequencies means such that L by lambda ratio or TR by T ratio will become significant. So that's what you have to keep in mind. Understood? So here at DC or at low frequencies, what is the resistance offered by a conducting material? What you are going to write? What you are going to write generally? So it is nothing but rho L into what? Rho L into A. Rho L divided by what? Rho L divided by A. So that is L by what? L by sigma into A. So rho is nothing but resistivity. So resistivity I can write it as 1 by conductivity. So L by sigma into what? L by sigma into A. Understood? Okay. So here in general whenever you are dealing with a DC resistance here, see here the conductivity, this conductivity is going to be what? Is going to be very large. This conductivity is going to be very large when compared to what? When compared to this L by A ratio. Understood? So in that case what we can do here, what we can assume, since the denominator is very large, so this value will tend to what? This value will tend to 0. So we can approximate the DC resistance approximately equal to what? Equal to 0. Yes or no? We can approximately take the DC resistance offered by what? Offered by the conductor is equivalent to what? Is approximately equivalent to 0. So this is what we can consider. Okay. So whenever we are dealing with what? DC means DC are at low frequencies. Understood? So low frequencies means you have to understand that, right? Okay. Okay. So under DC or at low frequencies, we can simply consider the resistance offered by the conductor is approximately equal to what? Approximately equal to 0. This is what we can consider. Understood? But at high frequencies here, at high frequencies, okay, what do you mean by high frequencies? Such that L by lambda or TR by T becomes what? Significant. So this is what always you have to keep in mind. So this is the last time I am going to specify this. Okay. Okay. So high frequencies are, so at high frequencies the resistance offered, we call it as what? We call it as RAC. RAC. Okay. So at high frequencies the resistance offered by the conductor, we call it as what here? RAC. RAC. So what is the, so in general what is the RAC? What is RAC? So that is AC resistance. AC resistance. See here, we know that for a good conducting medium here, for good conducting medium. See here we are dealing with what? Here we are dealing with the transmission lines, which is a good conducting medium. Yes or no? So in general, for good conducting medium, while studying uniform plane waves here, you would have studied that for the intrinsic impedance for a good conducting medium, is equal to what? Is equal to square root of j omega mu by what? J omega mu by sigma. Square root of j omega mu by sigma. I hope you know this relation here for good conducting medium. So if you don't know also, please take it as granted. Okay. So for good conducting medium, the intrinsic impedance offered by a good conducting medium is equal to what? Square root of j omega mu by what? J omega mu by sigma. Understood? Okay. Okay. Yeah. So anyway, we are going to derive all these things whenever we are dealing with what? Whenever we are going to deal with uniform plane waves, propagation of uniform plane waves in different media. So whenever we take the topic, there I am going to derive all these things. So don't worry about that. Okay. So but as of now, just take it as granted. So for a good conducting medium, the intrinsic impedance is equal to what? Square root of j omega mu by sigma. So this one I can write it as what? I can write it as square root of, sorry. So this one I can write it as what here? I can write it as square root of omega mu by 2 sigma plus what? Plus j into square root of what? Omega mu by 2 sigma. Can I write in this manner here? Tell me. See here how I have written square root of omega mu by sigma. Omega mu by sigma. So root j means it is at an angle what? Root j means I can write it as it is at an angle 45 degrees. So this means e power j 45. E power j 45 means cos 45 plus j sin 45, that is 1 by root 2 plus j by root 2. So if you multiply square root of omega mu by sigma with 1 by root 2 plus j by root 2, you are going to get what? You are going to get this result. You are going to get this result. Okay. So now if you observe this real part here, this is the real part of what? This is the real part of the impedance. So the real part of the impedance is nothing but what? Is nothing but the resistance. The real part of the impedance is nothing but what? Is nothing but resistance. Yes or no? Okay. So this resistance, generally we call it as surface resistance here. This resistance we call it as what here? Surface resistance. Okay. So this RS, what we are getting here? Square root of what? This RS is equal to square root of omega mu by what? Omega mu by 2 sigma. Omega mu by 2 sigma. Now there is a relation between RAC and RS here. RAC and RS. So RAC is equal to RS into what? RS into L by W, where L represents the length, W represents the width. Understood? Okay. Okay, L represents the length of the conductor and W represents the width here, width or thickness, right? Okay. Okay. So, so here if you observe RAC, so RAC is equal to what? Is equal to square root of omega mu by 2 sigma, omega mu by 2 sigma. So here you are having omega, here this is width here, this is width. So I am representing this with T. Okay. T, or you can represent with D. We'll use some other notation here because here I am using omega. Okay. So here okay. So here I am representing W. Okay, not omega. This is not omega, this is W, right? Okay. So L by W into what? Into L by what? L by W. L by W. Now if you observe here, so this omega is nothing but what? This omega is nothing but 2 pi f into mu by what? Mu by 2 sigma into L by what? Into L by W. So this is RAC. Now if you observe this RAC, that is at high frequencies, the resistance offered by the conductor is directly proportional to what? Is directly proportional to square root of what? Square root of frequency. Yes or no? It is directly proportional to square root of frequency. So that's what we can observe here. So RAC is directly proportional to what? Is directly proportional to square root of frequency. So that means as frequency goes on increases here, as frequency goes on increases, the resistance offered by the conducting material will also goes on what? Will also goes on increases. Understood? So under AC conditions, that means at high frequencies here, at high frequencies, the resistance we call it as what here? RAC, and we have observed that RAC is directly proportional to what? Is directly proportional to square root of frequency, square root of frequency. Understood? Okay. Okay, so square root of frequency. So that means at high frequencies, if you consider a conducting material, so the resistance offered by this conducting material at high frequencies is proportional to what? Is proportional to square root of frequency. So that means as frequency goes on increases, the resistance offered by that conducting material will also goes on increases, Understood? So since here we are dealing at high frequencies, the resistance offered by the conducting material will also be what? Will also be high. Yes or no? So that means now this resistance is not present at a particular location. Yes or no? We don't have the resistance only over this region, or we don't have the resistance only over this region. Understood? Okay, so this resistance is distributed. Yes or no? This is the resistance offered by what? Offered by the total conducting material. So that means this resistance is distributed throughout what? Throughout the length of what? Throughout the length of the transmission line. Yes or no? What is the difference between a lumped circuit element and the distributive element here? What is the difference? See, lumped circuit element means whenever we are drawing the circuit here, we are going to draw like this. Yes or no? Okay. So we are going to draw like this. So here this is conducting material, this is conductor, this is conductor, this is conductor. So what is the resistance offered by the conductor? The circuit theory is valid at low frequencies. Yes or no? Okay. So under low frequencies, the resistance offered by the conductor, that is RDC. You can approximately take it as what? RDC is equal to what? RDC is equal to 0. You will consider the resistance offered by the conductor is equal to what? Is equal to 0. Understood? So here, if you want to consider the resistance, that resistance is present only in this region, Yes or no? It is not distributed throughout the circuit. The resistance is present only at this location. Understood? If you want to place another resistance, you can place somewhere here. So this resistance is present only in this location. Okay, so this type of resistance we call it as what here? Lumped. Okay, so here the resistance is present only in this region. But here, if you consider a conductor, the resistance is distributed. The resistance is not located at any particular location. Instead, the resistance is distributed throughout what? Throughout the length of what? Throughout the length of the transmission line. Understood? Okay. Okay. So So that means whenever we are dealing with transmission lines, we are going to deal at high frequencies. So at high frequencies, the resistance is proportional to frequency, square root of frequency, and hence the resistance offered by the conductor, the resistance offered by this total conducting material is distributed throughout what? Throughout the length of what? Throughout the length of the transmission line, and hence what are the units of this resistance here? What are the units of this resistance? So the resistance simply we will represent with R. Okay, and what are the units of this resistance? What we are going to consider? See, I want to represent this resistance independent of what? Independent of length of the transmission line. So irrespective of the length of the transmission line, I want to define this resistance. So then what is the that means how I can define that? See, if I define the resistance per unit length here, okay, so if I define the resistance per unit length, then independent of the length of the transmission line, this resistance per unit length will be fixed or not? Yes or no? See, if I say 5 ohm per meter here, if I say resistance R is equal to 5 ohm per meter. Now, irrespective of the length of what? Irrespective of the length of the transmission line, the resistance I can say simply 5 ohm per meter. Understood? See, whenever something is distributive in nature here, whenever something is distributive in nature, the meaningful way of representing, representing the parameter is in terms of what? Is in terms of density, Okay, so that is the resistance we are going to represent as what here? The resistance that is distributed per what? Per meter. So this is the meaningful way of representing the resistance of transmission line. See, why means, if suppose for the transmission line, if the length changes here, then every time you have to change the value of what? Change the value of resistance. Understood? So if the length of the transmission line changes, then every time you have to represent the resistance offered by that length of the transmission line. Okay, so instead, if you just specify the resistance per unit length, then whatever may be the length of the transmission line, this resistance per unit length will be fixed. Okay, so that means we are defining the parameters which are independent of what? That are independent of length. Understood? Okay, so this is the meaningful way of representing the parameters whenever something is distributed like this, right? Okay. So I hope you have understood this point here. See, if it is not clear, please let me know here. I can repeat that. Okay. See, anywhere if you are getting any doubt, please let me know so that I can repeat that again. Okay. So that means if you consider a transmission line, then the resistance will be distributed along what? Along the length of what? Along the length of the transmission line. So here we are going to define the resistance of the transmission line as in terms of what? In terms of ohm per what? Ohm per meter. That is the resistance distributed per meter. Understood? Okay. So okay, so the resistance is going to be distributed along the length of what? Along the length of transmission line. So we have understood about resistance. Next, we will see inductance here. Okay. Now if I consider the transmission line, let us say here applied signal V, and here this is load. Okay, so here whenever you apply a signal here at the source end, so there will be a flow of what? There will be a flow of current. Understood? Okay, so that current is a function of both space as well as what? As well as time. So let us consider only time function. Okay, so let us consider we know that it is varying with respect to time as well as what? As well as space. Now I am considering with respect to time. I am doing the analysis with respect to time. Understood? So now whenever the current is flowing in the transmission line, let us say it is varying with respect to what? With respect to time. Let us say it is varying with respect to time, and here the current is flowing like this here. Understood? So whenever the current is flowing like this, it is going to produce what? It is going to produce the magnetic field. So above this line, the magnetic field will point out of the board, and below this line the magnetic field will point into the board. Yes or no? Okay, so similarly the current is flowing here. So if the current is flowing like this, understood, then the B field here is going to point what? Is going to point into the board, and here the current is flowing like this. So if the current is flowing like this, B field is going to point into the board. So that means here the current is flowing in which direction here? The current is flowing in clockwise direction. Understood? So whenever the current is flowing in clockwise direction, the B field is going to point in which direction? The B field is going to point into the board. Understood? Okay. Funny, once repeat it, sir. Resistance per unit length. Okay, I will explain this inductance part. Okay, so see the resistance per unit length. Why we are representing this resistance per unit length means, see, if you represent it per unit length here, if you represent it per unit length, then we are not worried about the length of the transmission line, whatever the length of the transmission line. Okay, so you can simply define what? You can simply define the resistance that is distributed per unit length. Yes or no? See, if suppose let us say I have considered a transmission line here. I have considered a transmission line. Okay, now I am saying the length of the transmission line is 50 meters. Let us assume the length of the transmission line is 50 meters. Understood? Now, if I want to define the resistance of this transmission line here, okay, if I want to define the resistance of this transmission line, so then I can say, see, it is made up of, let us assume it is made up of some conducting material, yes or no? This transmission line is going to made up of some conducting material, and the resistance it is going to offer, if I say simply 5 ohms here, if I say simply 5 ohms, understood? Okay, let us say I have said here 5 ohms. Okay, I have represented here 5 ohms, understood, for this conducting material, let us assume. Now, I am using the same conducting material here. I am using the same conducting material, but now I am changing the length. Now I am changing the length of the transmission line. Now here, let us consider L is equal to what? L is equal to, I am considering 100 meters. Now I am considering L is equal to what? L is equal to 100 meters. So now, if I change the length here, then what will happen here? The resistance offered by this conducting material will also changes or not? Yes or no? Yeah? See, I am defining the resistance. This is the total resistance offered by this conducting material, that is 5 ohms here. Understood? Now, for this length, it is 5 ohms. Now, if I change the length, I am using the same conducting material, but just I have changed the length. Now, in this case, the resistance may be what? Let us say this is R1. Now, here the resistance may become what? Resistance may become 10 ohm or 20 ohm or something. Okay, so it will become what? It is going to be different from this one. So that means every time if you use the same conducting material, still you are using the same conducting material, but whenever you are changing the length of the transmission line, you have to define each and every time its resistance. Understood? So instead of that, if I say simply the resistance offered by this conducting material in terms of what? In terms of ohm per meter. Let us assume I have said that R is equal to what? R is equal to 0.5 ohm per meter. If I said 0.5 ohm per meter, the resistance offered by this conducting material is 0.5 ohm per meter. That means on this conducting material, if you consider a unit length or unit meter length, understood? So over that unit meter length, what is the resistance that is present here? 0.5 ohm. Understood? So over a unit length, the resistance that is distributed is 0.5 ohms. Understood? So that means this is irrespective of what? Now this is irrespective of its length. Now for this one, so if I use the same conducting material, so for this one I can say simply the resistance offered by this transmission line is, I can say simply 0.5 ohm per meter. Here also I can say simply R is equal to what? R is equal to 0.5 ohm per what? 0.5 ohm per meter. 0.5 ohm per meter. Understood? Okay, so the resistance that is distributed per unit length is not going to change. Understood? Okay, so irrespective of the length, I can define what? I can define the resistance. Right? Okay. Okay. Understood? Funny? Yes or no? Yeah. Funny, I hope you have understood this one, right? So please give some comment here so that we can proceed. Yes? Okay. Okay. See, the same principle you will apply whenever you are calculating the power and all those things, yes or no? See, whenever you are calculating power, you always calculate what? Average power, or whenever you are calculating voltage, you are going to calculate VRMS, and whenever you are calculating current, you are going to calculate IRMS, yes or no? Okay, so you are not going to calculate instantaneous power value. You are not interested to calculate instantaneous voltage value and instantaneous current value. So what happens here, if you want to calculate instantaneous power, okay, instantaneous power means at each and every instant that power is going to change with respect to time. Understood? So if you want to define instantaneous power, you have to define the time also. Yes or no? So at this instant, what is the power? At this instant, what is the power? At another instant, what is the power? Like that you have to define, which is very much complicated. Understood? So that's why we will define what? We will define average power. So now, irrespective of time here, irrespective of time, you will get what? You will get some number here. Yes or no? P average is equal to, if I say simply 50 watts, if I say simply 50 watts. Understood? So you can understand, irrespective of the time, you are going to get what? You are going to get some number. Understood? Okay? Okay. So here also VRMS, if you say V by root 2 or some 5 by root 2 or something, so you are getting some number which is irrespective of what? Irrespective of time. Right? Okay? So which is something meaningful, right? So instantaneous values is meaningless here, because I may say the power at some instant and some other person will say the power at some other instant. Understood? So we don't get any brief idea about the power. Understood? So that's why we will represent in terms of its average value. Whenever we are representing voltages and currents, we represent in terms of what? RMS values and all. Okay? Why means we are making it independent of what? Independent of time. Right? Okay. So the same concept here, also. Right? Okay. Here we are making it, we are expressing the things independent of what? Independent of length. Right? Okay. Okay. So now coming to inductance. Now here I have applied a voltage source. And here the current is flowing. Now let us consider only time variation here. Let us consider. Understood? So whenever the current is flowing in clockwise direction like this. Understood? So the B field is going to point into the board. Right? So B field is going to penetrate into the board like this. So the B field is going to point into the board. Okay, so whenever the current is flowing, a time varying current is flowing like this, okay, it is going to produce what? It is going to produce the B field that is going to penetrate through this loop, and that B field is penetrating into what? Into the board. And we know that the number of magnetic field lines that are penetrating through this loop is nothing but what? Is nothing but magnetic flux. Yes or no? Okay. Okay. Yeah. So now what happens here? Whenever the current, here the current is varying with respect to time here. And hence the B field that is penetrating through this loop will also varies what? Will also varies with respect to time. So the magnetic field that is penetrating into the board will also varies with respect to time. Okay, so whenever the B field penetrating through this loop varies with respect to time, that means there is a change in magnetic flux. Through this loop. So whenever there is a change in magnetic flux, we know that from Faraday's law, whenever there is a change in magnetic flux, it is going to induce what? It is going to induce an EMF around this closed loop, and that EMF is going to produce what? EMF is going to produce an induced current. Understood? Okay. Now here let us assume I of t is increasing here. Let us assume the current that is flowing through the circuit is increasing with respect to time. Let us assume. So then what will happen here? The B field that is penetrating through this loop will also increases with respect to time. So that means the magnetic flux that is penetrating through this loop is increasing with respect to time. So whenever the flux is increasing here, whenever the magnetic flux is increasing, okay, what I have told here? The induced magnetic field direction will always what? Will be always opposite to what? Opposite to actual magnetic field direction. I have explained this in Faraday's law. Understood? You can go through that previous lectures here. I have explained all these things clearly while dealing with what? While dealing with Faraday's law. In EMT, each and every topic is interlinked to one another here. Understood? Okay. Okay. So in order to understand this subject clearly, you have to, there is no other way, you have to go through previous lectures also, right? Okay. Okay. So if I assume the current is increasing with respect to time, then the B field that is penetrating into the loop will also increases with respect to time. So that means the magnetic flux is increasing with respect to time. The magnetic flux that is pointing into the board is increasing with respect to time. So from Faraday's law, we know that whenever the magnetic flux is increasing with respect to time, then we know that there will be an induced magnetic field, and the direction of that induced magnetic field must be what? Must be exactly opposite to the direction of what? Direction of actual magnetic field. So actual magnetic field is pointing into the board, so induced magnetic field has to point out of the board. Yes or no? So B induced is going to must point out of the board. B induced must point out of the board. So this is B actual here. This is B actual. It is pointing into the board, and B induced has to point out of the board. So if B induced is pointing out of the board, then what is the direction of the induced current here? The direction of the induced current must flow in which direction? Must flow in anti-clockwise direction. Yes or no? Must flow in anti-clockwise direction. So that means here the induced current must flow in anti-clockwise direction like this. Understood? Okay. Okay. So that means what you can observe here. So whenever this current tries to change with respect to time, there will be a change in magnetic flux here. Because of this change in magnetic flux, there induces an EMF around this closed loop. Which is going to produce this induced current, and this induced current is opposing what? Is opposing this actual current, actual change in current. This induced current is opposing this change in current. See, if there is no change in current here, then there will be no change in magnetic flux. If there is no change in magnetic flux, then there won't be induced EMF, then there won't be induced currents. Understood? Okay, so since this current is varying with respect to time, so and hence there will be a change in magnetic flux in this region. So whenever there is a change in magnetic flux, there induces an EMF around this closed loop, which is going to produce what? Which is going to produce this induced current. So we have determined this direction of induced current with the help of what? With the help of Lenz's law. Yes or no? So what is that here? Whenever the flux is increasing into the board, the direction of induced magnetic field must be what? Must be exactly opposite to the direction of actual magnetic field. So that means here B induced is going to point out of the board. If the B induced is pointing out of the board, it is going to produce the induced current in anti-clockwise direction. So that means this induced current is opposing the change in what? Opposing the change in actual current. Understood? Okay. Okay. So that means here this total transmission line or this loop is opposing what? This loop is opposing the change in what? The change in current. Yes or no? So this loop is producing the induced current, which is exactly opposite to what? Exactly opposite to this change in currents. Understood? So that means I can say this loop is opposing what? This loop is opposing the change in currents. Understood? Now we know that the property of an inductor. What is the property of an inductor here? Inductor will always what? Will always opposes the change in currents. Yes or no? So that means this total loop is offering some inductance. This total loop is offering what? Is offering some inductance. Yes or no? Okay. So why are? Because this loop is opposing what? Is opposing the change in currents, and that is the property of what? That is the property of an inductor. Right? Okay. Okay. So that means this total loop is offering what? Is offering inductance. is offering inductance, right? Okay. Okay. Okay, so that means if you consider the transmission line, this total transmission line is offering what? Is offering the inductance. So the inductance is distributed along what? Along the length of what? Along the length of the transmission line. Right. Okay, so what are the units of the inductance here? Since it is distributed along the length of the transmission line, what is the meaningful way of representing the units here? Or what is the meaningful way of representing the inductance? The meaningful way of representing inductance is in terms of what? Is in terms of Henry per what? Henry per meter. Understood? Okay, so Henry per meter, right? So whenever you are having a transmission line like this, so whenever you apply a time varying voltage signal, there will be a flow of time varying current. So whenever there is a flow of time varying current, here there will be in this loop, within this loop, there will be a change in what? There will be a change in magnetic flux. Whenever there is a change in magnetic flux, there induces an EMF around this closed loop, and that EMF is going to produce what? An induced current. Now if you want to know the direction of induced current, then what you have to do? You have to apply what? You have to apply Lenz's law. So from Lenz's law, what we have studied here, whenever here the flux is increasing into the board. So whenever the flux is increasing into the board, then the direction of induced magnetic field, must be exactly what? Must be exactly opposite to the direction of what? The direction of actual magnetic field. That means here the induced magnetic field has to point out of the board. So if the induced magnetic field is pointing out of the board, then the induced current is going to flow in anti-clockwise direction like this. Okay, so actual current is trying to flow in clockwise. Now this induced current is trying to flow in anti-clockwise. So that means this induced current is opposing what? Is opposing this change in what? This change in actual current. Understood? Okay, so the opposition to the change in currents is the property of what? Is the property of an inductor. So that means this total loop is offering what? Is offering some inductance. Understood? So that means along the transmission line here, this inductance is what? This inductance is distributed. And whenever something is distributed, what is the meaningful way of representing it here? The meaningful way of representing it is in terms of what? It is in terms of Henry per what? Henry per meter. Understood? Okay. Okay. Whenever something is distributed throughout the length, the meaningful way of representing that quantity is in terms of per meter. Understood? Okay. Okay. So this is inductance. So that means on the transmission line, we have seen that the resistance is distributed. Along what? Along the length of the transmission line, and its units are ohm per meter. And similarly, the inductance is also what? Inductance is also distributed along the transmission line. Its units are what? Its units are Henry per meter. Understood? Okay. Okay. So next see here. Next here, this is one conductor and this is another conductor of the transmission line. Understood? So we are going to apply what? We are going to apply a potential difference between these two conductors. Yes or no? We are going to apply some signal here or not? Yes or no? You are going to apply some voltage source across these two conductors. Yes or no? So that means we try to maintain some potential difference between what? Between these two conductors, right? Okay. Okay. So now see here. Okay. So let us assume it is at some potential V1 and it is at some potential V2. Let us assume. Right. So there exists a potential difference between what? Between these two conductors of the transmission line. So let us say it is at some potential V1 and let us say this is at some potential V2. Let us assume V1 is greater than V2. Let us assume V1 is greater than V2. So that means this conductor is at some higher potential and this conductor is at what? Some lower potential. So whenever it is at higher potential and it is at lower potential, what is the direction of electric field here? What is the direction of electric field? The direction of electric field will be always from where to where? From higher potential to lower potential. So in this case, the electric field in this region is going to point in downward direction. Understood? What I am considering here, we are having transmission line. So here you are having one conductor and another conductor. Okay, so we know that these two conductors are maintained at what? Are maintained at two different potentials. Understood? Okay, so we are assuming that this conductor is at a potential V1 and this conductor is at a potential V2. Let us assume. Understood? Okay, and I am assuming that V1 is greater than V2. That means it is at higher potential and it is at lower potential. So that means whenever it is at higher potential and lower potential, we know that there will be an electric field. There will be an electric field between these two lines. Yes or no? And what is the direction of electric field here? The direction of electric field must be always what? Must be always from higher potential to lower potential. It is going to point like this. Understood? Okay. Now, what is the medium that is present between these two conductors here? The medium that is present between these two conductors is nothing but what? Is nothing but a dielectric medium. A dielectric medium. Understood? Okay. Now, let us assume it is not a perfect dielectric. Let us assume it is not a perfect dielectric. Understood? So what do you mean by not a perfect dielectric here? If it is not a perfect dielectric, then that means what? That means the conductivity of this medium, is not equal to 0. Let us assume the conductivity of this medium is not equal to 0. Okay, so it is not a perfect dielectric. Okay, I am considering in general we don't have a perfect dielectric medium. Yes or no? Okay, so in general the medium between these two conductors will be what? Will be dielectric in nature. And if I consider it is not a perfect dielectric medium, so that means there will be some conductivity associated with that dielectric medium. Yes or no? So if it is not a perfect dielectric medium, means its conductivity is not equal to 0. So what do you mean by conductivity not equal to 0 here? What do you mean by conductivity not equal to 0? So conductivity is not equal to 0 means some free charge carriers are available in this medium, Yes or no? See, whenever I am saying or whenever I am talking about conductivity, so what do I mean by conductivity? So conducting nature means in that medium we are going to have what? We are going to have free charge carriers. Yes or no? Okay, so here I am considering sigma is not equal to 0. So that means the conductivity of this medium is not equal to 0. That means it is having some finite conductivity. So if it is having some finite conductivity, that means some free charge carriers are available in this medium. Understood? So whenever there exists some free charge carriers in this medium, and here in this medium, what happening here? What is happening? Electric field is pointing in downward direction like this. Understood? So whenever electric field is pointing in this direction, and if some free charge carriers are available in this medium, that is going to cause what? That is going to cause some conduction currents or not? Yes or no here? So whenever you are having some free charge carriers in an electric field, what they are going to do? They are going to move or not? Yes or no? So if the free charge carriers are moving, then it is going to produce what? It is going to produce some conduction currents. Yes or no? But here generally this conductivity is not equal to 0, but it is what? It is almost negligible here. Understood? See, which nature of the medium is going to dominate in this region? The dielectric nature of the medium is going to dominate in this region, but it is going to have some conductivity which is very less. Okay, but it is not equal to 0. So if it is not equal to 0 means some free charge carriers are present. So because of this free charge carriers, what will happen here? You are having here electric field. So because of this electric field, this free charge carriers will start moving, which is going to give you what? If the free charge carrier starts moving, then it is going to contribute for what? It is going to contribute for conduction currents. So these are going to produce what? These are going to produce conduction currents. So here JC is not equal to what? JC is not equal to 0. So where JC is equal to what? JC is equal to sigma into what? Sigma into E. Here we have considered sigma not equal to 0, and you are having some electric field in this region, so which is going to cause some conduction currents between what? Between these two transmission lines. Okay, but we can ignore this conduction currents here, Why? Means these are going to be very less. Why? Means in general in this medium the dielectric nature of the medium will be very much dominant over what? Over the conducting nature of the medium, and hence the conduction currents will be present, but they are in very less amounts. Understood? Okay, so that's why these currents, these conduction currents that are flowing between these two conductors, we call them as what? We call them as generally leakage currents. Generally we call them as what here? Leakage currents. Understood? Okay, so why we are getting here? Why we are getting this leakage currents? Because here conductivity is not equal to 0. So that means there exists some conducting path between what? Between this line and this line. But those currents are what? Those currents are very, very negligible. So that's why we are calling it as simply leakage currents. Leakage currents. Understood? Okay. Okay. Yeah. So that means if you consider a transmission line, two conductors. So across this conductors, if it is not a perfect dielectric medium between the two conductors, if it is not a perfect dielectric medium, that is sigma is not equal to 0, in this case there exists what? There exists some conductance between what? Between the two lines, Okay, so this conductance is not only located at this location, it is going to distribute throughout what? Throughout the transmission line. Yes or no? Okay, so here throughout the transmission line you are going to have what? Across the transmission line there will be what? There will be a conductance. There will be a conductance which is represented with what? Which is represented with Z. Understood? Okay. Okay. So if sigma is equal to 0 here, if sigma is equal to 0, then conductance will also become equal to what? Conductance Z will also become equal to 0. Understood? So if it is a perfect dielectric here, if it is a perfect dielectric, then there will be no currents, then there will be no leakage currents, or then there will be no conduction currents. Understood? So in that case Z will become equal to what? Z will become equal to 0. There will be no conducting path between these two lines. Right? Okay. Okay. Yeah. Right. So what are the units of this conductance here? What are the units of this conductance? The units of this conductance, this is distributed throughout the transmission line, So it has developed between the two conductors and it is distributed throughout what? Throughout the transmission line like this. Understood? So what are the units of this conductance here? Mho per what? Mho per meter. The units of this conductance is mho per meter. Right? Okay. Is this point clear here? Tell me. Is this point clear? Please let me know, is this point clear? Okay. So if it is clear, next we will move on to next one. Right. So we have seen the resistance is distributed. The resistance is distributed throughout the transmission line. Inductance is distributed throughout the transmission line. And now we have seen the conductance. The conductance will be developed between the two lines and it is also distributed throughout what? Throughout the transmission line. So the units of resistance is ohm per meter. The units of resistance is ohm per meter. The units of inductance is Henry per meter. The units of inductance is Henry per meter, and the units of conductance is mho per meter. Right? Okay. Okay. So this distribution of inductance you will understand clearly if you would have followed my Faraday's law lecture here. Understood? Okay. Okay. Next, so two conductors. So we know that these two conductors are going to maintain at two different potentials, and these two conductors are separated by some dielectric medium, Yes or no? Okay. So whenever you are having two conductors, which are maintained at two different potentials separated by some dielectric medium, will offer what? Tell me. Whenever you are having two conductors, right, separated by some dielectric medium, and these two conductors are are at two different potentials. Whenever you are having two conductors maintained at two different potentials separated by a dielectric medium, will offer what? Will offer capacitance or not? Yes or no? It is going to offer a capacitance. It is going to offer a capacitance, right? Okay. Okay. So so we know that this is at some potential and this is at some other potential. Understood? So two conductors maintained at two different potentials separated by a dielectric medium will offer what? Will offer capacitance. Yes or no? Okay. So two conductors maintained at two different potentials, maintained at two different potentials separated by some dielectric medium, offers what? Offers capacitance. Okay. So these are the two conductors maintained at two different potentials separated by some dielectric medium. So this offers what? This offers a capacitance. So that means there will be a capacitance. Between what? Between these two conductors. There develops a capacitance between these two conductors, right? Okay. So if you take a transmission line, so across this transmission line there will be a capacitance. There develops a capacitance between these two lines, and this capacitance is distributed throughout what? Throughout the length of what? Throughout the length of the transmission line. So this capacitance is developed across what? Across the transmission line, and it is distributed throughout the transmission line. Conductance, previously we have seen conductance is also developed across the transmission line and it is distributed throughout the transmission line. And resistance is distributed throughout the length of the transmission line, and inductance is also distributed throughout the length of the transmission line. Okay. Okay. So here this is nothing but what? There develops a capacitance. So which we will represent with what? Which we will represent with C. What are the units of C here? So here this is distributive in nature. So if it is distributive in nature, what is the meaningful way of representation? That is in terms of what? Farad per what? Farad per meter. Farad per meter. Right? Okay. Okay. So now we have seen that the resistance is distributed along the length of the transmission line, inductance is also distributed throughout the length of the transmission line, and conductance is distributed along the length of the transmission line, but this conductance is developed between what? Between the two lines or across these two lines. Understood? And capacitance is also developed across these two lines and it is distributed throughout the length of the transmission line. Understood? Okay. See, these are not the parameters, these are not lumped parameters here. These are distributive parameters. Yes or no? These are distributed throughout what? Throughout the length of what? Throughout the length of the transmission line. They are not located at any particular location. They are distributed throughout the length of what? Throughout the length of the transmission line. That's what you have to keep in mind. Right? Okay. Okay. So that means here, that means here the resistance is distributed, throughout the length of the transmission line. Inductance is also distributed throughout the length of the transmission line, and the conductance is distributed throughout the transmission line, and the capacitance is also distributed throughout the length of what? Throughout the length of transmission line. Right? Okay. Okay. So the units of R is ohm per meter, the units of L is Henry per meter, the units of conductance is mho per meter, and the units of capacitance is farad per meter. Right? Okay. So now from this I am going to develop a circuit model. From this I am going to develop a circuit model for the transmission line. I am going to develop a circuit model for the transmission line. Okay. Okay. So now if I consider the length of the transmission line, as delta x here, if I consider the length of the transmission line as delta x, then what is the resistance? What is the resistance that is present throughout this length of the transmission line here? Tell me, what is the resistance that is present throughout the length of the transmission line? See, R represents what? R represents the resistance per unit length. Now I am considering the length of the transmission line as delta x. Then what is the resistance? What is the resistance present throughout the length of the transmission line? Tell me, what is the total resistance of this delta x length transmission line? Tell me, is nothing but what? R into delta x. Yes or no? So here I am considering R into what? R into delta x. R into delta x. So R into delta x is not the resistance that is located at this location. It is the resistance that is distributed throughout what? Throughout the length of what? Throughout the length of the transmission line. Understood? This is a distributive resistance. It is not a lumped resistance. Yes or no? So that's what you have to understand. Here I have represented the resistance which is distributed throughout the length of what? Throughout the length of the transmission line. So per unit length, if the resistance is R, then throughout the transmission line, the total resistance will be R into delta x. Yes or no? Now, next, similarly, the inductance is also distributed along the length of what? Along the length of transmission line. Understood? So, if I consider the length of the transmission line as delta x, then what is the inductance? What is the total inductance of the transmission line? Is nothing but what? Is nothing but L into what? L into delta x. L into delta x. You have to always keep in mind that this resistance is not located at this particular location. This resistance is distributed throughout the length of the transmission line. That's what you have to keep in mind. Understood? Okay. And similarly, inductance also. It is not the inductance that is present at this particular location. This is the inductance that is distributed throughout what? Throughout this length of the transmission line. Right? Okay. Okay. Just I am developing its equivalent model. That's it. Right? Okay. Okay. So next similarly, what is the capacitance here? What is the capacitance? So the capacitance is nothing but what? The capacitance that is distributed over this delta x length is nothing but what? Is nothing but C into what? C into delta x. And what is the conductance? What is the conductance? Conductance is nothing but Z into what? Z into delta x. Z into delta x. Okay. So this is the equivalent model. This is the equivalent model of what? This is the equivalent circuit model of the transmission line. Okay. So this is the equivalent model here. This is the equivalent circuit model. Equivalent circuit model of the transmission line. Okay. So it is not compulsory to represent only in this manner here. It is not compulsory to represent only in this manner. Why? Means we know that it is not located only at this particular location. It is distributed throughout the length. And similarly this one, similarly this one, similarly this one. Okay. So that means I can represent the circuit model in this manner also. So here I will represent R delta x by 2, and here I will represent L delta x by 2, and here I will represent C delta x by 2, and here I can represent Z delta x by 2, and here I can represent again R delta x by 2, and here I can represent L delta x by 2, and here I can represent C delta x by 2, and here I can represent Z delta x by 2. So like that here, like that I can represent the equivalent model in any manner, Understood? Okay. Okay here. So it doesn't matter here, because it is not the resistance that is this is not the resistance that is present only at this location. It is distributed throughout the length of the transmission line. So you can represent in any manner here the circuit model. It doesn't matter. Understood? Okay. But we try to represent in a simple manner so that the calculation will get what? The calculations will get simplified. Right? Okay. You can choose in any manner here. Right? Okay. Finally, the results are going to be same. Finally, the results are going to be same. Right? Okay. Okay. So here the voltage at this location, let us assume this location is x. So I am considering the potential at this location as V of x, and the voltage at this location will be what? Will be V of what? V of x plus delta x. V of x plus delta x. Right? Okay. So this is the we have developed a equivalent circuit model of the transmission line. Right? Okay. Okay. So with this I am winding up the session for today. Right? So tomorrow what we will do here is we will continue with this equivalent circuit model here. Tomorrow I am going to directly take this equivalent circuit model of the transmission line. So from here we try to get the equations in terms of voltages and currents, understood, and we try to get the solutions of those equations, right? Okay. So all those things we will see in the tomorrow's session here. So with this I am winding up the session for today, right? So we have developed what? Today we have developed equivalent circuit model of the transmission line, right? Okay. So with this I am winding up the session for today. Tomorrow exactly at 10 a.m. we are going to have the class here, right? So daily in our Gate Academy Global channel, EMT class will be conducted daily at 10 a.m. right? Okay. So tomorrow we will continue from here. Tomorrow we will continue from this equivalent circuit model of the transmission line, right? Okay. So with this I am winding up the session. So tomorrow we will meet exactly at 10 a.m. So until then, take care. Bye bye.